Before I start, let me just make one more quick comment, repeating what Wina said. So far on the web page, the whole data is only based on those algebraic structure and also three differentials we put in by hand, two in very high filtration, very high stem in the image of J, and one differential in the computation of Brunner algorithms in the Adams flower sequence of TMF. And if we look at the infinity page in codes, you still see a bunch of dash differentials, unknown ones in this version of the data, but there are known arguments in the literature. So we have other non-public versions which we manually put in these differentials and use the program to propagate and get more information. But the public version is good enough for the argument for 126. So we're keeping this version for now. So another thing, as Vina have said, is that so the plot on the web page only gives you partial information versus the computer generated data. So for example, if you look at this is stem 126, and there is a dash D3 on the web page. It says D3 of this is unknown, but actually, if you go to the E3 page, there are a bunch of dots. So there are, I guess, 3 dots. So there are 8 possibilities in total. The computer program cannot fully determine the last possibility, but it can rule out a bunch more. So in particular, if you click on this dot, you see it has a non-zero H2 multiple supporting a non-zero D3 differential, and it's coming from this dot times H2. So therefore, we actually know that this is a non-zero D3 differential. It's killing precisely this dot or this dot plus this dot on the right. So it's in particular, it's a non-zero D3 differential, and the remaining possibilities can be read off from the data on the nodal, but it's not showing up in the chart. All right, so now let me start. So I'd like to talk about the final arguments for the existence of theta 6. So namely, theta 6 survives to the infinite page. So for notations, let me fix a few notations. So if I have x in x, which is a permanent cycle, we use this symbol, the curly bracket x, to denote the set of all classes in the homotopy that are detected by x. So as long as x is not the highest atom filtration in that stem, this set usually contains more than one element. And when it is of the highest atom filtration, it's precisely one non-zero element. I use this square bracket to denote a class in the set. It could be either a specific one, which I will have to define it, or a general class, depending on the context. So for example, my notation for theta 5 is the homotopy class is detected by H5 squared. I'm using these notations for both classical and synthetic. So synthetically, it is still in stem 62, and the weight is 62 plus its atoms filtration, which is 2. Okay, and I'm using this to detect any, like a general class detected by H5 squared in the atoms E2 page. And I'm abusing the notation to use SID5 to denote both this homotopy class in the synthetic sphere and also the mapping to cofiber of lambda to the R for any R greater or equals to 1. So similarly, eta is my homotopy class, any synthetic homotopy class in pi 1, 1 plus 1. So here's the fact that we know of the synthetic theta 5, which is that any choice of the synthetic theta 5 has order 2. So why that is true? Let's take a look. So first of all, we can deduce this bigrid group does not contain any lambda torsion. So let me get back to a chart and to the E2 page. So recall that how the rigidity of the synthetic atom spiral sequence work. So in general, every dot on the E2 page, it corresponds to a homotopy class in the same stem, and the weight is the stem plus the atom filtration. And when I multiply that by lambda, it's in the same stem, but the weight will be decreased by 1. So on the picture, you can view lambda as going down by 1, just for the right by degree. Technically speaking, it's in the homograph point, so the Adams filtration of lambda is still 0, but you can think that as some sort of Adams filtration minus 1, if you like. So a D2 differential will leave the target with a single lambda torsion. A D3 differential will leave the target with a lambda squared torsion. So therefore, having this D2 differential, this target is still there, but it doesn't have any lambda torsion to stay. And as in a comparison, if you have a D3 differential, this style will still be here, and it will still have a single lambda torsion, which shows up in the location 1 down there, but not lambda squared, because lambda squared will be killed. So it behaves like all Adams differentials look like an Adams D1 differential, hitting the right lambda tower. So now let's restrict attention to theta 5, H5 squared. So synthetically, this lives in the bigraded homotypic group, and contributions from could have dots in higher filtration. If you have a lambda free, like a classically surviving element, so this dot in filtration 6, then it's lambda to the fourth power. Lambda to the fourth power times this element will still contribute to this bigraded synthetic homotypic group. However, for all the portion elements, as you can see, since 63,0, there's nothing in here. If there were having a dot supporting, say, a D3 differential, then this dot will have a lambda torsion, lambda multiple contributing to things here, which is a lambda torsion. But since there's nothing here, all these differentials, they're corresponding, the lambda torsion they create does not contribute to this pi degree. So in conclusion, in this pi degree, it's going to be completely from lambda-free things, okay? So, and also classically, a theorem mine, also computation with Isaacson and Wang, we computed that in fact, the whole pi 62 is Z-mod 2 direct sum with itself 4 times, okay? So every theta 5 has order 2, okay? So this can be, so in the infinity page, there are 4 dots left, infiltration 2, 6, 8, and 10, and this one does not admit any 2 extension, does not support any 2 extension, okay? So therefore, combining these two facts, we know that any synthetic theta 5 will also have order 2. All right, so there is this inductive approach for theta 6 by Barrett, Johnson, and Howard, upgraded by Berkland and myself in the synthetic setting, which states that theta H6 squared survives to the ER plus 3 page in the classical Adams filter sequence, even only if for some synthetic theta 5, this expression lambda e to theta 5 squared in this bigraded homotypic group on this page is 0. And in particular, it is a permanent cycle if for some theta 5, this expression is 0. So one thing you see from the proof is that this expression, regardless of the choice of theta 5, is consistent in the synthetic homotypic groups. So I will say a few words of how we prove this. The idea is the following. So take any synthetic theta 5, it is of order 2, so I can extend it to the mod 2 Moore spectrum. So this is the mod 2 Moore spectrum with the right bi degree. And then I can take the quadratic construction on the mod 2 Moore spectrum and map it down to sphere. And here is a picture for it. So left-hand side is the mod 2 Moore spectrum where restriction to the bottom cell is theta 5. And right-hand side, I take the quadratic construction of the mod 2 Moore spectrum and restrict attention to a certain subcomplex, and that's the corresponding attached maps. So by the way, synthetically, when we smash with covariant lambda, namely restricting attention to the Adams E2 page, all the attaching maps in RP infinity, they're all lambda divisible. In particular, 2 is lambda divisible. 2 equals to lambda times H0. Okay, so all the cells split off, so it becomes a vector of spheres. That's the corresponding Brunner's power operation on the Adams E2 page. But before we smash with covariant lambda, we work in the synthetic homotypic group. These are the attaching maps. So moreover, knowing the information on the E2 page, we know precisely what happens on X. So in other words, non-homotypy. So we know the non-homotypy as the input is H6, that's the half invariant 1 differential. And in here, by computing the stimuli operations, the power operations on the E2 page, we know this non-homotypy is H6 squared, and this one further down is H7. So in the Barrow-Jones-Mahoward argument, if one knows that theta 5 squared is 0, then we can just ignore this bottom cell and have this two-more spectrum mapping to the sphere using H6 squared as the bottom cell map, and therefore we obtain the existence of theta 6, and it is of order 2. And in here, we can just restrict attention to the bottom two cells with the attaching map eta squared, lambda squared eta, and read off the non-homotypy, which encodes the total Adams differential. And the non-homotypy here on the left-hand side, H6 squared is a fixed unique homotypy class because that's in the X, okay? And it is, of course, lambda torsion, so it maps to a lambda torsion, and the lambda torsion is precisely this expression. And it does not matter which choice we have to start with the theta 5. We can always do this construction, and they have the same value in here. And this tells us that if eta theta 5 squared is detected by some element in the Adams E2 page, the synthetic Adams E2 page, we have some power of lambda to adjust for the synthetic weight to match with this expression, then we obtain a synthetic Adams differential of this form. And by inverting lambda, namely, we just ignore this term, we get back to a classical Adams differential. So in particular, if this expression is 0 in this, this expression is 0 in the synthetic homotypic groups of spheres, then we know theta 6 survives. H6 squared is a permanent cycle. Is H6 squared the product of theta 5 squared with lambda eta or lambda squared eta? So what happens is that because of these two attaching maps, so we know for sure that the multiplication of these two things is 0. And the total differential maps to a single lambda torsion. So if we know lambda times eta theta 5 squared is 0, then we know H6 squared is a permanent cycle. Okay. All right. Just as classically, we know automatically eta times theta 5 squared is 0, no matter what, classically. But synthetically, we need to figure out precisely how torsion that is. Okay. All right, so the strategy of proving theta 6 as a permanent cycle is to give an Adams filtration estimation, right? So the goal is to show this expression is 0 by an Adams filtration estimation. So you can think the second grading is a way to estimate the Adams filtration. So we start with this part. We start with theta 5 squared. So this lives in stem 124, and presumably the Adam filtration is 4, but we know H5 to the 4th power is 0 on the E2 page. But now we can also just look at the E2 page. So this is 124,4. So there's nothing here, right? So presumably it is in here. From the same logic as I said before, in 125, in lower X Adams filtration, there's nothing here. If there is something here support a differential, then that would create a lambda torsion. So this whole thing could be detected by a lambda torsion, but there's nothing here. So that's telling us this bigraded synthetic homotypic group does not contain lambda torsion. So therefore, if theta 5 squared is non-zero, it has to be detected by something classically, something which is lambda free. So now let's look at, now we can just ignore all the torsions and look at the actual infinity page, the leftovers. So in 124, the lowest filtration that has a dot is the filtration 10. It has this name, H0 square X 124,8. So we know for free that, well, from Vinan's program computations, we know the Adam filtration is at least 10. When it is 10, there's only one dot left. It is precisely this dot, right? So this one has Adam filtration 4, this one has 10, so I have to adjust things by lambda to the power of 6. So next, let's multiply that by eta and try to estimate what happens to eta theta 5 squared. Okay, So let's move on to the next column. Okay. So if I just look at the infinity page, we see that, well, there's no H1 multiplication here, so it go beyond that. And if I'm just looking at lambda free part, it will go to filtration 14. But it could be detected by a lambda torsion, right? A lambda free element multiplied by eta, it could be detected by lambda torsion. So I have to be careful. I have to deal with all the lambda torsion elements. So maybe let me remove dash all to make it smaller. Okay. So this dot here, H0 squared x 124.8 is the candidate for theta 5 squared. Okay. When I multiply by eta, it goes to this spot in 124,11, which since there's no multiplication on the E2 page, it has to go above, right? So for the 5 dots in filtration 12, the left two support differential, so I can ignore that. The other three are killed by D3 and D2, right? So in order to get rid of that, I have to multiply by some power of lambda to get rid of that. Similarly, in filtration 13, there's one supporting a differential. These four are killed by D2 or D4s. So therefore, if I multiply this thing by e the cube, then I can just get rid of all the torsions, then go to the next filtration. The next filtration in 14, there is this dot, which I do not know the answer of, which could be a lambda-free element. So therefore, when I multiply by eta and also lambda cube, I know the filtration will jump to at least 14. When it is 14, there's only one element, and it is this element in filtration 14. And when it is above 14, then it is 0. So again, I have to adjust for all the torsion elements, but you can just by inspection, they're not going to interfere with this argument. And if I go beyond 14, there's only this dot in TMF. Sorry, this dot is in TMF. And as Vin mentioned in his talk, that this D4, although it doesn't show up on the web page, it supports a non-zero D4 differential, making the only dot left here is detected by TMF. Since theta 5 is mapped to 0 in TMF, and therefore I don't have to worry about this element detects eta times theta 5 squared times lambda to the right power. So in other words, the only eta extension I need to worry about is this dot in filtration 14. Okay, so here is the proposition, and that's the name left in filtration 14. So exactly one of the following two statements is true. It's either that theta 6 survives, or it supports a non-zero D12 differential to this element in 14. So this is a classical statement, so I don't have lambda in here. And moreover, the second statement, this non-zero D12 happens if and only if the following three statements are all true. So in order for this element to be a non-zero differential, I need to first require that this element is not killed by a shorter differential. Upon inspection, we see that this element in filtration 8 is the only possibility to kill it. So classically, this is a leftover. So that this dot is the one I want. So if I click on this dot, it shows it's a permanent. If I click this dot, that's the possible D6 in filtration 8. So it could support the D6 killing this dot in dimension 14. So one next to it, it supports a very long differential. But due to the same TMF story, we actually know this D7 does not happen. So this is a permanent cycle. There are also total brackets arguments to show that. So this element is a similar one. It's a permanent cycle. It goes to 25 and it's TMF. And this one is a non-zero D3 differential I was just telling you about. And then the only other possibility is H6 squared. So in other words, the only possibility to kill this element in 14 is a permanent cycle, is this D6 or the D12. So the computer program so far, we do not know the answer of this D6. So if we were to have an argument saying that this is a non-zero D6 differential, then we're done. There is a much simpler argument. Then it's directly, so this is a D6, and this dot will disappear. We just multiply with more lambda power, and therefore we can just conclude that eta theta 5 squared is 0. So condition 3 is one to guarantee that this expression is non-zero on the E12 page. So basically what I just showed you earlier is that the lowest filtration that could detect theta 5 square in dimension 124 is this element in filtration 10. We do not know whether or not that is the case. When that is the case, when I have this relation, and furthermore, there's this eta extension from 10 to 14, namely from this dot to this dot in filtration 14. Only when these two both happens together with this D6 is 0, we are able to have this non-zero D12 differential. So basically, I have already explained to you the proof for this proposition. So another comment is that whenever I write this, so the precise statement should be read as the following. For any choice of theta 5 squared is always detected by this element, and in particular, it's a non-zero element. And similar for this statement, for any choice of a homotopy class detected by this element, when multiplied by lambda cube times eta, they're detected by this element in 125,14. So it turns out the choices in these two statements, it does not matter. They don't matter. So that can be proved by just checking the local data to make the argument. So I will conclude the proof of proposition A by proving the following proposition B. Namely, so all I need is to show that one of the 3, 4, and 5 is not true, and therefore ruling out this non-zero D12 differential and conclude that H6 square survives. And the way to do that is, since I do not know whether or not 3 is true, I'm assuming it is always true. And under that condition, I'm proving that this eta extension cannot happen, and therefore proving that set 6 exists. So in the rest of this talk, I'm going to sketch the proof why this eta extension cannot happen. So for the sake of contradiction, let's assume this eta extension does happen. So I'm going to list 4 lemmas. But before I state what they are, so let me give you a sketch proof on the web page. So I'm trying to assume this eta extension does happen and deduce a contradiction. So one natural thing to use is to make use of this eta here. So one caveat is, of course, I do not know this element survives, but I do know it survives to the E12 page. So therefore, I will make the argument not in the synthetic sphere, but in the synthetic sphere modulo out by some power of lambda. Okay, and when I'm making an argument over there, then I have this eta square extension. And furthermore, I'm trying to argue that on that page, on that S mod lambda to the 9, actually, I'm making the argument not on lambda S mod lambda to the 11th power, but on the 9th power, because the 11th power argument does not work for some reason. This element has order 2. So as we know, whenever we have an element of order 2 and times eta square is non-zero, then its eta square multiple has to be divisible by 2. And then by some local argument, I can show that this is the only possibility to support that 2 extension. We do not know this element survives to the corresponding page, but under the assumption, we will force this element to survive to the next page and having this 2 extension. Then I'm using the generalized Malhover trick to find a differential in Kervaire nu to show that there is a new extension from this dot in 122,8. Again, this argument has to be made on a certain page because I do not know this element as a permanent cycle. And therefore, I have a new and a 2 extension. Then I can also consider this dot first have a 2 extension, then to a new extension. So in the end, I will see that the only possibility for this dot to have a 2 extension, not going to filtration too high, are these 2 dots, and they're both permanent cycles. And then that will force a new extension from one of these 2 dots to this dot, and that contradicts with the Kervaire nu data. So that's basically the sketch of the proof. So let me say this one more time. So I'm proving by contradiction that I'm assuming this extension happens, and on a certain page, this dot survives and has order 2, and therefore I multiply by eta squared has to be divisible by 2, and that dot is the only possibility. And there is a new extension can be proved otherwise. So I have a new and 2 extension. And then I translate that to first consider 2 extension and new extension. And in the end, it gives a contradiction to Kervaire nu. So the precise statement has to be made on certain pages. So first, I will restrict attention to this element alpha 1 detected by this blue dot. This element survives to eCHT page. Okay, so the claim is that this alpha 1 when I multiply by eta, so that's the dot of interest that could detect theta 5 squared. Okay, so when I have this dot times eta and theta 5 squared detected with the same element, they could be differed by elements of higher filtration. So that, therefore, there is the existence of alpha 2, and these are the elements, the right power to adjust for the weight. And this alpha 2 is actually, at least in this filtration and this dot, it accepts a 0 H1 multiplication on E2 page. So therefore, when I multiply that by eta, it is divisible by lambda. And then I further show that this element has order 2 in the right page and right degree. So that's first lemma. So since I have this relation, the second lemma would be I can form a synthetic total bracket. And this is the part when I shuffle this total bracket is eta squared is 2 eta 2. And for degree reasons, by just studying the local data, this is like a strictly defined total bracket with 0 indeterminacy. I can conclude that it does not contain 0. It's detected by this element, h0 squared x 125, 9, 2, namely this dot. Okay. And then as a consequence, this dot will support a h0 extension to this element of interest in filtration 14 as a corollary of lemma 2. And finally, I establish a new extension, as I mentioned earlier, to this dot and draw a conclusion, and draw a contradiction. So here's a sketch proof of proposition B. So this dot h1 x 121, 7, which is this dot, okay? So assuming all the four lemmas I mentioned are true, when I multiply by h2, it becomes this dot. Further multiplication by h0, it becomes this dot, okay? And by assumption of that d6 differential is 0, this expression is actually, this element is actually non-zero. This is in filtration 14, and multiplication by eta to the 6. If that d6 differential does not happen, this is a non-zero expression, even if h6 squared supports a non-zero d12 differential. This expression is still non-zero. Then in particular, this expression has to be non-zero as well, and lives in this bi degree. And looking at all the possibilities, I have two dots left. These are the two candidates that could be the h0 extension on this dot. Okay. So one thing to note is that both of these two dots are permanent cycles. Okay, and they are not hit by any differential. So they actually live in the synthetic sphere. They're lambda free. So therefore, for either one of them, I multiply by h2 gives me this element, and this relation holds in the sphere, not just in lambda mod lambda to the 9. And therefore, I can lift this relation to the synthetic sphere. So in both cases, I obtain the conclusion that this target in 125, 14 has to be a new multiple. And that contradicts, that will force that in Kervaire, this element has to be killed by a differential of length smaller or equals to 5. And now if I look at the data of Kervaire in dimension 125, 14. So that's the dot, h1, h4, x1, 09, 12, 0 from the bottom cell. So I need to know that it's not killed by any D2 differential. So these are all accounted for. So for these three, so that's the D14 unknown. So in particular, does not support the D3. That's a permanent cycle. So these two are permanent cycles. It doesn't support D3 killing it. And in here, all these three are accounted for. It doesn't support D4. In here, these four are accounted for. This one supports D16 unknown, so it doesn't support D5. So it's not killed by D2, D3, or D5, D4, D5, and therefore it contradicts with that argument in the end. So the argument is very subtle. You see that we do not know if there's a D6 killing it, but that differential will be the same differential happens in sphere, which could lead to a much easier argument. All right, so maybe let me just briefly give you the flavor of how these lemmas are proved. So they're all like technical arguments in the local data, and synthetically, we have a lot of differentials from the computer programs and give us a lot of lambda torsions as leftovers. So basically, the classical shuffling total brackets or ad hoc arguments can also work in here. So for the first lemma, I'm trying to establish that this alpha 1, when I multiply by eta, it's this element plus some higher filtration element. So first of all, this element survives to E12 page. I'm back to the sphere. So this element survived to the E12 page. So on the E2 page, when I multiply by H1, you see that its H1 multiplication is the sum of these two dots. So it's not the same as this candidate for theta 5 squared. However, their difference is Q by D2. So that means they're the same on the E3 page and beyond. So now when I multiply, so that's why I want to first multiply it by eta. So these two will be the same on the E3 page, and the D2 difference is creating a lambda torsion. So I further multiply by eta, and this expression leaves in a higher Adams filtration. And just to get rid of a few higher Adams filtration element, but the lambda torsion, I want to multiply with lambda squared furthermore, and I can draw the conclusion it is at least at a filtration 13. And if that's the case, that is precisely this element in Adams filtration 13. So this dot times eta goes up. I multiply some lambda tower to get rid of all the torsion elements, and there's only one possible lambda-free element in here that's in filtration 13. Okay, and that's our candidate for alpha2. It's unknown that whether or not this expression is detected by this element. If it's not the case, this will have an even higher lambda power to it. Okay, and since this element, when I multiply by H1, is 0 in X, and therefore I also have this expression. So this expression can be also checked by just studying the corresponding group and corresponding Adams filtration. So one subtle thing is here is that I can have an Adams filtration estimate to see that this one has Adams filtration at least 17, and therefore, but this element lives in 7. So therefore, it must be a lambda to the 10th power multiple. And therefore, this expression, when I project to lambda to the power of 10 or lambda to the power of 9, it becomes 0. And that's why this 9 here is very critical in here. So that's the proof of lemma 1. For lemma 2, I'm studying a synthetic total bracket. It is well defined because of the relation I mentioned earlier. So the argument, roughly speaking, is the following. So the reason I want to study this total bracket is because of the shuffling. So 2 eta 2 is eta squared. And this relation on eta squared comes from the previous lemma. When I multiply this eta extension, it gives me this element precisely. And since this expression is non-zero, and so therefore this expression is non-zero, but its H0 multiple is in filtration 14. So therefore this element is at most in Adams filtration 12. Then I can just study the corresponding chart, look at for all the candidates in Adams filtration 12 and adjust it for the correct lambda power. Then later on, I rule out these two candidates and draw the conclusion that this one has to be the case. And in particular, due to the shuffling, it also gives me lemma 3 that we have this H0 extension in here. And finally, for lemma 4, I'm trying to establish this H2 multiplication. So this is done precisely by the generalized Mahover trick. So namely, so first of all, I'm using this power here because this element survives E6 page. So therefore, in the E9, in lambda to the 9, this element, if it supports a non-zero D6 differential, then this expression would kill lambda to the 5th times that, which is lambda to the 9 and is already 0. And therefore, this element actually survives in the Adams spiral sequence for S0 mod lambda to the 9. Okay, so this is a legitimate homotopy class. Then to study its H2 multiplication, I started the Kervaire. So I have the line that sequence. This is a non-zero D3 differential in the Kervaire given by the computer program. Using the generalized Mahover trick, I obtained this H2 extension. But note that this only happens in the sphere mod lambda to the cube. What I wanted is this relation in Kervaire of lambda to the 9, what's happening is that I first lifted it back to sphere mod lambda to the fifth power. So there need to be some local argument to be made in here because this is true in mod lambda to the cube. So presumably in mod lambda to the fifth, it could be this term plus lambda cube multiple of something else. Then I need to look for the right bi degree to list all the possibilities and rule them out one by one. And it turns out in the end, in S mod lambda to the fifth, I still have this relation. And then I further use this map to push it down to lambda mod 9, and that's the final argument. All right, I'll stop here.